learn like a pro.
Okay, so picture this. You've got a pile of salt just completely mixed in with a pile of sand. How in the world would you separate them? I mean, it seems basically impossible, right? Well, in chemistry, there's a surprisingly elegant solution, and it all comes down to a kind of invisible gatekeeper. So let's dive in and see how it works. So here's our game plan. First, we'll look at the unmixing problem itself. Then, we'll introduce our main tool for the job, filtration, and see what's happening at the microscopic level. After that, we'll add a clever little twist with something called solubility, and then put it all together in a master plan to separate a really complex mixture.
All right, so here's our starting challenge. A mix of sand and salt. You can't just sit there and pick out every single grain one by one, right? So, where do you even start?
Well, the first step is to kind of change the nature of the problem. We do that by adding a solvent, and in this case, plain old water works perfectly. See, the salt dissolves completely in the water, but the sand, it doesn't. And just like that, what was a solid-solid mess is now a solid-liquid mixture, and that sets us up perfectly for the next step.
And that brings us to our most important technique, filtration. It's a really simple but incredibly powerful way to separate a solid from a liquid. And trust me, this technique is used absolutely everywhere. The actual setup couldn't be simpler. You've just got a funnel, a flask to catch the liquid, and of course, the real hero of the whole operation, the filter paper. We just pour our mixture right through. The solid gets trapped by the paper, and the liquid drips down into the flask. Now, there are a couple of key terms for these two parts that we need to know.
First off, the solid stuff that gets left behind on the filter paper, that's called the residue. In our example, that's the sand, and an easy way to remember it is that it resides on the paper. It stays put. And the liquid that actually passes through the filter, we call that the filtrate. So for us, that's the salt water. So let's recap real quick. Residue stays behind, filtrate goes through. Got it? Simple.
So, how does the paper actually do this? Is it some kind of magic? Nope, it's actually way cooler than magic. It all comes down to one simple thing, size. And to really see what's going on, we need to zoom in. I mean, way in.
And here it is. If you look at filter paper under a powerful microscope, you'd see it's not a solid sheet at all. It's a tangled web of fibers full of teeny-tiny holes, or pores. You can think of it like a microscopic bouncer at a club with a super strict policy. You must be this small to get in. And the rule is just dead simple. If a particle is smaller than the pores, like the dissolved salt particles, it just slips right through with the water and becomes the part of the filtrate. But if a particle is bigger than the pores, like our chunky grains of sand, it gets stopped flat. It's too big to pass through the gate, so it becomes the residue. That's it. That's the entire secret. It's all about size.
So you can see that solubility, the ability to dissolve, is what gives us control. By dissolving something, we can basically shrink it down until it's small enough to pass through our filter. But here's the twist. Not everything dissolves in the same liquid. And knowing this, well, this is where we can get really, really clever.
Okay, check this out. Let's imagine we have three new solids. We'll call them P, Q, and R. Now, solid P dissolves in both water and ethanol. Solid Q, on the other hand, only dissolves in water. And solid R, it's stubborn. It doesn't dissolve in either one. These unique properties, these solubility profiles, are going to be the key to solving a much harder puzzle. It's all about picking the right tool for the right job.
Let's test this out. Okay, if we mix P and Q together in water, can filtration separate them? Nope, because they both dissolve, so they both just pass right through. What about P and R in ethanol? Yes, absolutely. P dissolves and goes through, but R stays behind. Okay, how about P and Q in ethanol? Yes, again, P dissolves, but this time Q stays solid. And one last one, Q and R in water? You got it. Q dissolves, R doesn't. You see the pattern? For filtration to work, you need one substance to dissolve and the other one not to.
All right, it's time for the final boss. We've got a mixture of all three solids, P, Q, and R, all jumbled together. A single solvent isn't going to cut it this time. For this, we're going to need a multi-stage master plan. So here's our strategy, our plan of attack. It's a two-step process. First, we're going to use ethanol specifically to pull out solid P. Then we'll take what's left over and use water to separate Q from R. Ready? Let's walk through it. Okay, phase 1. We add ethanol to our three-part mixture. Now, based on what we know, only P dissolves in ethanol. So we filter the whole thing. Solid P goes right through the filter paper, becoming our filtrate. We've isolated our first solid. And what's left behind on the paper as residue? Solids Q and R, stuck together. But we're not done yet.
Now, for phase 2, we take that residue, that mixture of Q and R, and this time we add water. Now what happens? Well, Q dissolves in water, but R doesn't, so we filter it one last time. Solid Q passes through as the filtrate, leaving behind pure solid R as our final residue. And there you have it, all 3 components perfectly separated.
And here you can see the whole beautiful process laid out. We started with the total mess, a chaotic mixture of 3 different things. And by using 2 carefully chosen solvents and 2 simple filtrations, we systematically pulled it apart, piece by piece. It's incredible, isn't it? By understanding these invisible, microscopic rules about size and solubility, we were able to create perfect order out of chaos. You know, this idea of using invisible principles to create order is so much bigger than just a chemistry lab. It's a fundamental concept that's all around us. So it makes you think, where else do we see this in action? Think about biology, with cell membranes acting as filters, or in technology, with algorithms that filter information for us, or even in our own societies. So I'll leave you with this to chew on. What are the other invisible filters that are constantly shaping our world?